Well, I kept on blowing fuses. I just finished putting the box on, and what I forgot to do was put in the 2 plastic spacers right in here between this and this heatsink. So if that one is in there, this hooks to ground. Works fine on an isolation transformer, but as soon as I hooked it up to mains, I had a ground loop.
And now for something completely different.
Well, the last thing I had done was place the power supply board back into its box and back onto the chassis. So my immediate thought that I must have disconnected another wire while doing this. And that wire must be shorting someplace, as I had had a couple wires come loose before when I've been playing with this project. Just as I got ready to examine the board for loose wires, I noticed my goof, and as I'd shown before, I'd put those silly plastic insulators on the wrong side of the mounting bracket for a pair of transistors. Once I fixed that, I tried another power-up and got nothing. Well, I spent the next long while, and I do mean a real long while, trying to figure out what parts I fried. So for the last few months, I've really just been wasting my time, checking here, checking there, riding one hunch against another hunch, checking everything with my multimeter and my new transistor checker, and generating pages of notes, tables, a few debug plans that all went nowhere. Now that the summer is over and our radio club is meeting again, I sat down and talked with one of the guys, schematic in hand, and asking for some sage advice. I had only just started to blurt out the hookup mistake I did, and he didn't even look at the schematic when he said, "Well, I have no idea what damage you could have caused and why it's not working. And looking at a schematic that I'm not familiar with is not going to get you the answer you're looking for." But the rest of his advice did ring true. First, take a break and come back to it with a clear mind. Second, it's a good thing that you know what you did wrong, and you've resolved the short, and you have the schematic. So start with your schematic, trace out what you did wrong, and that'll give you an idea where to start on the power supply. Once you have a starting point, work both ways in your schematic, checking each component as you go, and repairing any that might be damaged. And of course, test it each time you repair something. The final thing to say is with an old analog scope like this, you'll need to get the power supply working perfectly if you know if you've damaged anything else. So sage advice indeed. As you can see, the full power supply schematic is rather daunting at first glance. But the key takeaway is that this transformer in the middle divides the power supply into 2 separate parts. The right side that contains all the high voltages and heater voltages for the CRT, as well as the source voltages for the regulated 15, -15, and 5-volt power rails used in the brains of the scope. On the left side, you'll find the mains rectifying circuitry, and you'll also note that there's no transformer here, which is why I was always using an isolation transformer when I had the box open. And that's, of course, for safety. As the first priority is getting the power supply to work correctly, let's take a deeper look at the left-hand side. Now, the left side has a few other parts rather than just a simple rectifier. It has this part here, which is a regulation circuitry that puts out 123 volts. That 123 volts is used as the source voltage for the high voltage transformer. And it's also the source voltage for a 5-volt power rail, and that 5-volt power rail powers the multivibrator circuit. Now, the multivibrator circuit puts out a high-frequency square wave. Now, we still need an AC voltage to go into the AC transformer, and this is where the multivibrator steps in. The multivibrator ultimately turns on Q106 and 107, and that generates a 123-volt AC square wave, and that is passed into the transformers, and that generates the high voltage for the other side of the power supply. So my buddy was right. If the left-hand side of the power supply isn't working, the CRT and brains aren't going to work either. So it's best to check this side first, and if I get that working, then I can start on the other side. So concentrating on this part of the power supply, let's zoom in to where I made my mistake, Q106 and Q107. These are not TO3 packages, but they are similar in style, where the collector is on the shell, and the emitter and base each have their own pins. As you can see in the schematic, both have dash boxes surrounding them. And that should tell you that both Q106 and 107 are mounted off the board on a separate bracket, and that they are insulated from the chassis ground. Now in my earlier videos, you can see that I was carefully making sure that that bracket never touched ground anyplace, let alone the chassis. So I guess I was just in a real hurry to get it all back together, and didn't pay attention to the reassembly notes I had taken. Oh well.
Get on with it!
My first thought was that I had connected the bracket, and hence the collectors, to the common ground rail. However, when I took a closer look at the schematic, I noticed that the bracket is already connected to common, so that wasn't the source of my short. I had to zoom way out again to see what I did. By not installing those two insulators correctly, I ended up mounting that bracket directly to earth ground. Now there are literally dozens of spots on this scope that are connected to earth ground, so I might have caused a lot of damage. Now one might think, ground is ground, no problem, right? Well, no. Looking back at this part of the schematic, you can see the good old P101, or the mains plug, and you can see the ground connection coming off here. But of course here I am in North America, and that ground line goes up and somewhere into the bowels of my house, where it is connected back to the common side of the plug, so I actually get this. Now, as long as I was using an isolation transformer, I was fine, as there was never a connection between ground and common. Take that isolation transformer away, suddenly you've connected ground to common, and zap! Everything in red should be 0 volts. And after that short, I have up to 120 volts on the ground rail. Now, I recently discovered online the Falstad circuit simulating tool. It's a little Java applet that you run right from your browser, and I'll leave a link for it down in the comments someplace. Now, I found this applet quite useful in understanding what actually went on here. The simulation gives me a very clear picture of what's going on. If you look at it closely, you'll see two voltages, one on top and one on the bottom, and they drop from 120 to 0, or go up from 0 to 120. Notice you'll never see a negative voltage. That's because there isn't any. All there is a potential between 0 and 120 volts on one side, and its opposite on the other side. The simulator even shows this, because it doesn't really show any movement between the voltage on one side and the voltage on the other. Let's just say positive and negative are an arbitrary selection. And as I don't really want to get into a lecture on alternating current, I'm going to skip along to what it looks like when I made my mistake in the simulator. So all I have to do to simulate it is take one little line from here and add another wire into the bottom of my bridge rectifier, and zap! The simulator's hard stops with what it calls a max current exceeded, or basically a dead short. So the question is, what sort of damage could I have possibly done? Now the voltage I applied to that rail is 0 to 120 volts. And the maximum current was 1.5 amps, which was the largest fuse I used. Now I'm lucky in that the fuse blew instantaneously, but that's still about a quarter of a second, which is several cycles of 0 to 120 volts. So let's just take that maximum voltage of 120 and look at the differing parts of the circuit I might have fried. Now there's not much that could have gone wrong with the input components, like the bridge rectifier and the filtering capacitors, as they have a much higher working voltage than 120. Likewise, the regulating circuitry up here was designed to be used with 120 volts inputs, so I'm not worried about any components here. And again, we have this regulating circuitry down here, and that was designed for 120 volts, so I'm not worried about that one either. Now these two switching transistors are protected by these two crowbar circuits, so again, not worried about these. Finally, there is the regulator circuitry for the 5-volt supply. I'm not worried about the two transistors that make up the supply, but that Zener diode is giving me a lot of concern. From this examination, I now have two places where I can narrow down where I might have caused some damage. Here at CR109, and that should tell me if I'm having any problems in my bridge rectifier circuitry or the high voltage regulator. And over here at C114, which would tell me if my 5-volt regulator is working. There, that's set up so it doesn't short out on anything. Ready for our first test. I'm hooked up into CR109. We'll throw the switch. See what the voltage is. There, we can see that better. Alright, you can see that a little better there. And got it hooked up to the dim bulb tester. And I'm getting about 20 volts DC, which I should be getting 100 and something, so something's not going good there. Let's go try that 5 volt rail. Alright, set up for the next test on the next, this should be a 5 volt rail. And throw the switch. Whoa! Negative 32 volts. So something definitely not right in there. So let's go have a look-see. So as I kind of suspected, right near C15 is our Zener diode CR130. And that's shorted. Yeah, that would kind of screw up the 5 volt rail, and that would screw up everything else. That would stop voltage from going back through. That would explain why this resistor here is getting hot. Is it the resistor? Yeah, it's the resistor that's getting hot. So let's swap that out. So I've marked the spot where the diode goes in, and I'll just take that out now. There we go. While I am busily swapping out that diode, let's have a closer look at the schematic. So here's the Zener diode, and now it's a short, and so I'm most likely getting no current and only a negative voltage at this point. And if we have no current or positive voltage at this point, Q110 is not going to turn on. And if Q110 doesn't turn off, we're not going to get any current or voltage at this point. And if this point has no current or voltage, Q109 is not going to turn on, so therefore we're not going to get anything on the power rails. So hopefully the new Zener will fix that fault. DC volts. And we're getting negative 28 now, which is not nice. Time to go see if something else is burned out. Alrighty. I was getting the correct voltage. Negative 32 plus 5 volts gives me about negative 28. I just didn't realize it. Then I noticed my mistake. Not only did I get positive and negative swapped around, giving me the negative voltage, I was also taking the voltage to ground directly instead of the voltage across the Zener. Once I did that, I got the correct voltage. And of course now I was getting about 90 volts over here at CR109, and adjusting the regulator voltage control pot didn't have any effect. And of course I didn't get any of that on camera. At this point in the story, this is where the Falstad circuit simulator came in handy. And I was able to create an approximation of the full circuit, as you see here. The important takeaway is that I was able to get the correct voltage at my Zener, and the voltage at CR109 is about okay, but the main reason why it's low is because I didn't have all the different parameters for the transistors and their gain and whatnot. But it was a start. After playing around a bit, what I decided to do was simplify my simulation, and only simulate just the 123 volt regulating circuit, and that's what you see here. Now, as it was a much smaller simulation, I was able to put in all the proper parameters for the transistors, and I used the nominal voltage from the schematic, which was 180 volts. And as you can see, I'm regulating at 120 volts, and if I change the value of the resistor, I can change the value of the regulation. Now all I had to do was take out bits and pieces, or add some extra shorts, to see where the mistake might be. And what I was looking for was a voltage drop down to about 80 volts or 90. Anyway, here's an example of what I did. Went over and simply just took out the Zener diode, deleted that, and see what the result was. And of course my voltage is going up to 174. So we'll put that one back in. And of course, other things I tried was just taking them all out at once. And normally when a transistor died, my voltage would go up. Eventually, I was trying other things. For example, I was trying shorted diodes. This would be a shorted diode, just straight down to here, or let's just stick it here for now. And still getting 174 in that case. Down there. It's not the easiest one to work with because it's just playing with Java. And of course, what I eventually found out, going through this, taking diodes and stuff out doesn't really do much. Ooh, does drop that down nicely. However, it's dropping down too much in this case, down to 50 volts. So that's not the problem is. And if I let this go, it'll eventually drop down to almost nothing, down to 36 volt, which is the Zener diode here. I'll probably just stop at 36. Or maybe not. Put that one back in. Back up to 25. What I eventually discovered, and I can even take this one out, my voltage stays about the same. And I did test that one. Of course it was good. Now, after playing around like that for a rather long time, I was eventually able to find my possible problem. If this transistor here, Q103, had shorted and made a disconnection here, but also shorted the ground down here, come here, never take that off of there, and this one going all the way to ground here, you'll see the voltage starts to drop down to about 90 volts, or less even, 99, 98. So now I'm really suspicious. It gave me very suspicious of Q103. I'm going to go have a look at that one right now.
Oh dear. Unfortunately, the more you play with this, the more your chance of mucking something up. Now, I wasn't sure if this broke before or after, but I broke a pin off this NPN high voltage transistor. Turns out this MPS 10U was basically used in TVs as a high voltage switcher. What's it doing here? I don't know. I think any basic modern day switcher should work. I got a couple here. Two high voltage ones. So I'm going to swap that out for these and hope for the best.
Now, I did have a suitable replacement for the MPS U10, but the problem was the pinout. The U10 has the same pinout as a TO92 case, EBC, emitter-based controller, and the replacement transistor I had was a TO222, which was base controller emitter. So as you can see, as I'm trying to fit that in there, I had to do a lot of creative bending, plus a little heat shrink for good measure to get the replacement in there. And once it was all in there, I gave it another go.
Okay, on the dim bulb tester. Let's give her a shot. Hooked into mains directly, but through the dim bulb tester, no isolation. I'm getting something. Channel A position. Ah, there we go. Got a dot. Good. Yay! She's working again.
And there was much rejoicing.
Now with the power supply all fixed up and my trace back, I started what I think is my 5th attempt at calibrating the scope, and I was about halfway through, and the scope suddenly decided to release the magic smoke yet again. Of course I didn't get this on camera. This time round, it was not the power supply where the smoke was coming from, but the main vertical board. Youch! Fortunately, I was able to see what component was smoking, and it was way over here, this inductor, L210, which is really odd as it was coming right out of the power rail and onto the main switch. Now, the only way this inductor would burn up if there was a short somewhere along the power rail. From my notes, at the time of the smoke up, I knew that I had channel A off and channel B on. And since A and B use about 90% of the same circuitry on this side of the switch, and there was no magic smoke release on channel A, that means the short must be somewhere on this side of the switch. And that's where I found this.
So after some poking around and figuring about why I was getting it shorted when any switch was put in, right to ground, I noticed this. This wire right here. It was underneath that plate. So from the factory it was put in wrong. Oh dear. So I'll clean that up. Put some heat shrink on it. So it must have been done when they first started it. Obviously it was hard to pull out of there. It was under that plate. And as I've never had this plate off, that must be it. Anyway, factory defect.
As I'm fixing that wire and putting in a new inductor, I also took the opportunity to put in a new cap, as it was pretty much fried. The main note here is that the schematic is wrong. It says 10 nanofarads on the schematic, but in reality it's only a 1 nanofarad. Little things you have to watch out for. Now let's see what's going on.
There's the new inductor right there, and the new cap there. You can see the burn spot from the inductor. Let's get this tested now. So that means I should get 15 volts here. We'll see what happens. Okay, we'll flip that around and get all set up to test again. Power on. 14. Channel A, 14. There we go. No drop to 0. No short. Yeah.
And now back again to yet another calibration attempt. And I would love to say at this time it was the end of my story. But alas no. Channel B worked like a charm. However, I had this persistent problem with channel A. It just wouldn't trigger correctly on a few of the voltage setting.
I go to channel A. It's not triggering and I get the signal on it. So I'm going to set up my piece of paper, which I've got here, which lists all the places the signal path goes through. And I'm going to check and see what I see on the other oscilloscope. So you need an oscilloscope to test an oscilloscope. Here we go.
Before I went way too far down the rabbit hole yet again, I went to another radio club meeting and met up with the guy who gave me the sage advice from before.
Everything's cleaned up now. But I'm still not getting it to trigger correctly. Even on auto, it just goes off and on 1. So I was at the radio club the other night and asked one of the old guys, I was just chatting with one of the old guys, what was my problem. And he asked me 3 simple questions. Well, the first one, so it's a dual channel telescope. Do both the same channels use all the same circuitry? And I said, yeah, they all use the same trigger. So he said, test the other channel, channel B. Does it have the same problem? Nope, steady as a rock. Oops, sorry, wrong one. No problem at all. Only on that one value. He says, so it's not the trigger, it's something else. Then he asked, does your oscilloscope have a balance point? And he says, yeah, it's right there. I said, did you balance the oscilloscope? And he says, what's that? So, I didn't. Because it's hidden in the other thing, as you can see in the manual. Right there, it's hidden way up in chapter 2. So we'll do that right now and see what happens. Power off. Intensity. Position centered. Centered. Horizontal gain 1x. Mode, if that, A. Volts a centimeter 1. Okay. Switch channel A and B. 1. Variable channel A and B off. Check. Vertical input switch AC. AC. Invert norm. Norm. Okay. Invert under norm. TV norm. Plus minus on the plus. Plus. Auto norm on auto. Level centered. Time on 2 milliseconds. 2 seconds. Time variable clockwise. Power on. Okay. Take that off. Okay. Okay, so it says carefully put it in the center. Okay. And center it. Oop, 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 oop. Alright, that's centered. Let's try channel B. And that's nicely centered. So channel A. Move the 5-volt range. Ah, it's off the screen. And I bet in channel B on 5 volt, it's perfect. Yep. Recenter it with the position screen. Okay. Back to the 1 volt range. Adjust the balance again till it's on the line. Okay, and then back to 5. And up it goes. Back to 1. Then that comes down. Okay, now I see how this works. Okay. Getting close. There we go. Let's put in that 10k hertz and see what we get. There we go. Yeah, what's that? There we go. Ha-ha! No bouncing around. How about that? Triggering worked fine, even off auto.
Now that that is done, there is no real need for yet another calibration, as the last one was fine, and I'm really sick of doing them anyway. And I don't want this video to go on for any longer. As I put Humpty Dumpty back together again, it's time for a few last words. First and foremost, I did learn a lot in this project. I can now say that I am now very familiar with Zener diode and pass transistor regulator circuits. I now know way too much about export restricted items and how to get them out the US legally. I did discover the Falstad circuit simulator and how useful it is. I now have a very much better idea how AC voltage works, and how a severe ground fault will ruin your day. Of course, it's the old lesson of how important it is to read and actually understand the manual before you get started on something, not just skimming over like I usually do. Now, the big fail on this one was fully my fault. Even though I had taken good notes when I took the power supply out of its can, I failed to follow them when putting it back into the can. Not only that, I failed also to do a double check before I powered her up, something I normally always do, but this time I got in a hurry and didn't bother. I think the most important lesson I learned was to seek out and follow the advice of those that have been there before and learn from their wisdom. Finally, I am glad to report that this scope is now in good hands, being used to build and fix tube guitar amps.